This video continues and concludes the introduction to probability concepts in the CFA. So it is a little bit technical, but it's very much an introduction. So if you're already familiar with probability concepts, you don't need it. But as you know, I'm a big believer in getting the fundamentals right. So it's with my pleasure that we'll review portfolio expected value, the covariance and correlation. And because that's probably familiar to you, I'm going to try to introduce a few tips as we go along, having written and answered a lot of questions about covariance and correlation. We'll also look at portfolio, variance, and standard deviation, the special two-asset case that is so common in financial exams. And I'll make a brief mention of how that generalizes with a covariance or correlation matrix when we have n assets or positions. And finally, just a couple few basic topics in probability, including very briefly the base, theorem, and an application, and then some principles of counting. So I look forward to sharing that with you. This will be the final section of Introduction to Probability Concepts in the CFA Level 1. So the first concept is portfolio expected return. That's pretty straightforward. The expected return on the portfolio is a weighted average of the expected return of the component securities. And so for every component in the portfolio, we would have one term, and we're just stringing them together in a summation, the weight of the first component multiplied by its own expected return. So in this example here, the portfolio only has 3 assets. And a good gut check here is to make sure that our weights sum to 100%, right? 35 plus 20% is 55, plus 45% is 100%, so that's good. And then we're just implementing this here, this first weight of 0.35 multiplied by the expected return. I'm going to just put that in decimal form, right? That's our first term, plus here the 0.2 multiplied by 0.03 plus the 0.45 multiplied by the 11% here. So we only have the 3 terms, and if you did that in the calculator, you should get 10.45%. And a good gut check there is to make sure that that falls somewhere within the range here, the minimum max. The minimum here is 3, and the max is 14, so I do need to get an expected a weighted average that's somewhere between 3 and 14, which I do, so that's plausible. If I were to get a 2 for some reason, that would be a flag that I have an error. It's outside the range. It's lower than the minimum value here. Or if I were to get a 15, for example, I would have made some kind of mistake. So I sometimes think that some of those gut checks can be helpful along the way. The covariance, that's a little trickier. This is a measure of co-movement of the 2 variables, and so it's given here by this expression, which we could summarize in English in the following way. We could say it's the expected cross product. It's actually very simple to say it. Covariance is expected cross product. So in order to compute a covariance, we do need 2 variables. So now we have the return of A and return of B. Imagine those could be 2 positions in the portfolio. And instead of, these are weights, but we could think of them as probabilities. So where we only have 3 outcomes here, a 40% probability that asset A returns 25% and asset B returns 24%. That's a joint outcome. So you can see we only have here 3 outcomes with different probabilities. And I don't know about you, but visually, if you look at this, these are high outcomes here jointly, and then a lower outcome jointly. Visually, that does look like they have some positive co-movement. So I'm not too surprised to see a positive covariance outcome. However, be warned, covariance does not lend itself to interpretation. I've looked at a lot of covariances, and all I can tell you is that in terms of intuition, it's almost always very small number, sometimes very small. In fact, when I see a covariance, a calculation of something like 0.3, that's actually a flag that there's been an imprecise calculation. Oftentimes you expect to see 0.0 something or 0.003 is very much in the range because we're, as a very low number, plausible covariance, because we are going to standardize it into a more intuitive measure of co-movement. And that, of course, is the correlation, but I'll show you that soon. But here, in terms of implementing this formula, we need, for expectation, if we have the probabilities, these are ex ante expectations, so we have a fully specified distribution because of the fact that we have a summation of 100%, and we can do the cross product now in the following way. It's 3 rows though, 3 rows, 3 terms, and in terms of the first row, what I have is a 25% expected return minus the expected return for the variable, which is its own weighted average. That's a univariate statistic here. That 17.1 is just the weighted average like we looked at before, isolated on this first return variable A and its return. So its weighted average is 17.1. So we subtract it. See how that is just this return minus the common expected return. And then now the cross product means we multiply by, we do the same thing for B. 24 minus its expected return. So that's the cross product, and then I am going to need to multiply it by its weight, so 0.4, do that. And then we're going to add it now and do the same thing on the next row. So now we'll do the weight at first, 25% probability multiplied by the cross product. 20 minus, now here I'm reusing the same 17.1 because this is going to be the same throughout. And then over here, return on B, 18 minus the same 19.35. And I'm going to add that to finally the last weight, just gut checking that these add to 100%. If I were doing this for the first time, that's what I would do. 6 minus the same 17.1. multiplied by, I left out my little symbol operator there because that, when you do that, that implies multiplication. Multiplied here by, let's see, my last one, 15 minus that same expected return of 19.35. And if you did that, you should get 0.0031. And that, I believe, is the way that it is shown to be in the CFA syllabus, or the way that the math is shown. And remember, again, in terms of intuition, I would say we expect a very low number. What we can tell from this, though, is this positive, right? Positive instead of negative. And now what I'll show you what I think is a easier way to do the covariance. And mathematically, it's the same exact result. And it invokes one of, I think, the most important useful qualities, and that is that I'll just change variables, but now that is that the covariance here between x and y is equal to the expectation of the product of x and y minus expectation of x multiplied by expectation of y. So what do I have there? Well, in simple English, the covariance between x and y is the expectation of their product minus the product of their expectations. So that's very interesting. So that's why here I add a column, and all that I've done here is I multiply the weight, which again is our probability, that 0.4 multiplied by 0.25 multiplied by 0.24. So you see, I left out, I'm implying multiplication. Multiply these three together to get these three values. So that's weight times the respective probabilities, and then summing them here at 0.0362. What have I solved for? Well, I've solved for the expected product, right? Because that's 0.25 times 0.24 has a 40% probability. Then I'm adding product here multiplied by its weight, which is this. So if I add these together, what I'm getting here is the equivalent here, the expected product, or cross product if you like. And then all I need to do is subtract here from this the 0.171 multiplied by the 0.194. See, that's my expected x and expected y, the analogs here. So I take 0.0362, that's the expected product or cross product if you like, and subtract the product of their expectations, and you will necessarily mathematically get the same answer of the covariance. So this is my preferred way to do it. And this is the formula worth, frankly, memorizing because this generalizes the variance, right? So notice, let's say that x equals y, then what do we have here? We have or y equals x. We have the covariance of x with itself, which is the variance of x by definition, and it's going to equal the expected x squared minus the expectation of x quantity squared. That is a really helpful formula for variance, and hopefully I've shown you in a very intuitive way how that is simply a special case of this very helpful utilitarian covariance equality. And then so we have, if the covariance is negative, the returns on one asset is less than expected value, and returns on another asset is more than the expected value. That's the implication. If the covariance is 0, then the returns are unrelated. And then it's worth hovering on a point here that that covariance and correlation are measures of linear dependence. So if what we said here, if the covariance equals 0, to be mindful of the fact that's a linear association. So we don't want to say that if the covariance is 0, that these are independent. Right? Very tempting, you can see unrelated to say independent, but that's not correct because dependence can be nonlinear. So we can get a 0 covariance for variables that have some kind of association that's nonlinear. So they could be associated, but you still get a 0 covariance. So the key idea is if the variables are independent, then the covariance will be equal to 0, but we cannot say that if the covariance is 0, that they are independent. And again, that's because covariance is a measure of linear dependency, but independent means not dependent, and dependent is not just linear dependence, it's all sorts of nonlinear dependence. So the key difference there is linearity. The covariance of a random variable with itself is equal to its variance. I've already mentioned that. It varies between negative infinity to infinity. As I've said, for realistic data sets, tends to be closer to 0 than have larger values. And of course, it's difficult to interpret. Okay, so correlation, that's the famous one. It's the linear relationship between two variables, and I think I mentioned it before. The way I would describe it, one way, is that it's a standardized covariance. So we've taken that covariance in the numerator, difficult to interpret, and divide it by the product of the variables' respective standard deviations. And in doing that, we've done at least two things. We've standardized this into a value that lies between -1 and +1. And we've also, by the way, in doing that, made it unitless. And so then we get the correlation. And the advantage of this, of course, is that it's very easy to intuitive. Maybe the only disadvantage, among the two disadvantages are, again, it is linear. So we have that same trap that's easy to fall into, which is that if we see a 0 correlation, we might be tempted to say independent. The two variables are independent. I didn't write that very well, but we'd be wrong because independence is much broader than linear dependence. And so what we can really only say is the inverse, I suppose, or converse. If variables are independent, then the correlation must be equal to 0. So we have here the familiar interpretations. If correlation is +1, that indicates positive linear relationship. If it's -1, that indicates perfect negative linear relationship. And in realistic use cases, very difficult to get values close to 1 or -1. In fact, correlations that are above 0.9 in realistic data sets, I know we're always trying to achieve that, but that's when I start to raise a flag for me that there may be some data mining going on. So continuing with the previous exercise, we already calculated the positive but low covariance, and now to translate that into a correlation, if we've already computed the statistics, is very straightforward. We just take that covariance and divide it by the product of the standard deviations. 8.38 and 3.97, I put a parens around them, and that's a multiplier. The product of, these are the standard deviations, these are univariate standard deviations, so this is 8.38 is just that standard deviation of this variable itself, doesn't really involve B. It gets multiplied by the same standard deviation in B's case, and then we'll get here this, what to me would be a suspiciously high correlation in terms of data sets, although we have here designed probability distribution as ex ante with expectations, so we could easily design a high correlation, which we've done here. But it falls within, it's unitless, and it's very close to 1, so easy to interpret. The one thing I did here is include the same, this slide is the same exact problem set, although let me go back to the previous one, because I noticed this in the syllabus that the tendency here is to represent it thusly, where we have returns. This is a 25% return. And you may be luckier than me. You may just get away with without having to cope with this, but this comes up in a lot for me when actually solving problems, and that is to say, you'll see the problem represented that way. And of course, I'm sure you know that that's 25.0%, and of course we can represent it that way, but that's equal to 0.25. So in fact, that if you actually did pause and do that covariance calculation that we first showed, and you used in the calculator, used these raw, you used 25 instead of 0.25, you might have figured out that the result here was a much larger number, and you had to divide that number by 100 squared, because in decimal format, you effectively had retranslated these. So, but ignore that if you didn't have to cope with that. But I just did want to include a slide just to say that this problem set here, when I go to do it in a calculator, Excel for that matter, I must say that I much prefer dealing with the direct decimals, where I just don't have to confront that kind of translation problem that I did just with the calculator, right? We're never going to go wrong here. That's 25, that's expected return 25% is 0.25, and it won't lead us astray. We won't actually, if we do that covariance here, we won't actually have to do a translation at the end to account for the fact we started with numbers, if we started by putting a 25 in here, that in decimal format would have been inaccurate. Portfolio expected variance. This is a measure of portfolio risk. This is the mean variance framework, one of the most oldest and most commonly taught ideas in finance. And so the variance of our portfolio is given here by this formula, and its 2-asset version here is here. And this is, in terms of financial exams, extremely common to be tested on this. The 2-asset portfolio, you want to keep in mind that that's an unrealistically simple use case, so it avoids us having to deal with a matrix or linear algebra that would be associated with more realistic portfolios. But here we have, right, we have a variance, so we want to pay attention to the fact that sigma squared telling us a variance, not a standard deviation, and we have the weight of the first component squared multiplied by its variance, right? I could say variance, or I could say standard deviation squared, but so it's a standard deviation squared, I might as well say variance. Add that to the weight of the second component squared multiplied by its own variance. And then we have here this additional term, which will really capture the effect of the correlation covariance and really captures the effect of any diversification benefits. 2, we have a 2 out here in front due to the math, multiplied by the weight of 1, weight of 2, multiplied by the covariance between the two. And then I will say that it's important for us to be flexible with this and to remember that at any point, this covariance is the same as the standard deviation of R1 multiplied by the standard deviation of R2 multiplied by, I'm going to use that Greek rho to signify correlation between 1 and 2. And I'll do it like that. A few different ways to note that. My only point there is we have covariance here in this expression that we've chosen to, but this covariance could be computed by or replaced by its equivalent, which per that earlier formula, that covariance is just equal to the product of these three variables. Standard deviation of the first, standard deviation of the second, and the correlation between the two, right? So that's covariance. This is covariance here is necessarily a function of the correlation, or put in a way, the correlation is embedded in the covariance. So I won't go into the math here. I certainly have other videos on YouTube that show a 3-asset example, for example, but that 2-asset formula that tends to be common in exams, just keep in mind that that is a 2-asset case, a special case of an n-asset portfolio, where realistically our portfolio is more likely to have more than 2 positions, or I'd like to say more than 2 components. In this example, it might be 4 components equally weighted so that the weights are 25%. And then at that point, we do want to be comfortable with applying using the matrix math, which really generalizes that same formula, and in which case, right, we're going to have, instead of just a correlation in that 2-asset case, we had a correlation between 2 variables. The difference now is we have a correlation matrix that contains pairwise correlations. Here's a correlation matrix. The telltale sign of a correlation matrix is its diagonals must have 1s, because the correlation of A with itself must be 1. So we need to have diagonals, and then we really only have an upper or lower triangle because they are mirror images of each other. But in this correlation matrix, for example, I've got a value here of 0.17318. That is what I would call the pairwise correlation between position A and D. Right, so you see here my A and my D, 0.17. And because the correlation is symmetric, that means that A with D over here, see how this is you could call this, this might be referred to as DA, row column, and this might be referred to as AD, but they need to have the same correlations, the mirror images. So that's why I say the triangle is a mirror image of the triangle. And as far as unique, and this diagonal needs to be 1s, the correlation matrix. So here, with the 4 positions, we only have 1, 2, 3. I'll just erase these. 1, 2, 3, 4, 5, 6 unique pairwise correlations in my 4x4 correlation matrix. And no accident, actually that's a triangle number, and because the triangle number is given by n times n minus 1 divided by 2, which is in this case 4 times 3 divided by 2, which is 6. So that's how many pairwise correlations. And it's also, as the number matrix gets larger, that's also the reference to the curse of dimensionality. So I'm not going to go into the math, that just wanted to show you how that how we start to generalize that. And it's the same case here, the relationship between correlation and covariance. My covariance here matrix embeds the correlation matrix. And so it introduces also the weights and the volatilities, but there's a sense in which, just like in the 2-asset case, they are functions of each other. But again, that correlation matrix betrays itself by the fact that it must have 1s in the diagonal. And what did the covariance matrix, here's a good question for you. What do the diagonals of the covariance matrix need to be? Right, not ones, because what we have here is the correlation of A with the covariance of A with itself, which is its variance. So the diagonal of the covariance matrix needs to be variances, and therefore will likely be non-zeros and also very likely be non-ones. So that if we get to a problem like the following, consider a portfolio that consists of two stocks, stock A and stock B. Stock A represents 35% of the portfolio, that's right there. The standard deviation of stock A is 12%, while the standard deviation of stock B is 18%, and the covariance between the two is 0.035. Okay, wait, excuse me, I had to change that because I realized I didn't have a match. Now I got that back. The covariance between the two is 0.015. What is the portfolio expected variance and standard deviation? And you'll notice the problem, by the way, didn't give us the weight of stock B. That's 65%. That's because it didn't need to give us that. It told us it's two stocks and stock A represents 35%. Therefore, we need to figure out ourselves that stock B is 65% of the weight. So the portfolio expected variance just applies that formula that we looked at for the two asset portfolio variance. We're going to have three terms here, right? The first one is just going to be with respect to stock A. I'm just going to write it out. It's going to be the weight 0.35 multiplied by its standard deviation. I'm going to stay in decimals here. Let me start that over. Weight 0.35 multiplied by its standard deviation. I'll just use a multiplier here. But remember, it's weight squared multiplied by variance. So I could take that product here and square it because that's the same as squaring them both. Multiplying is the same difference. So that's for stock A. Then I'm going to add, same thing for stock B, 0.65 multiplied by 0.18. I'm going to make sure to square that. And then I'm just going to add what I think of as that diversification term. I need to make sure I remember that it has a 2 in front. And then I have the weight, 0.35. I'll do a multiplier times my 0.65 multiplied by what? Covariance, 0.015. If I didn't have the covariance, I would need to compute it possibly by taking the standard deviation or volatility of A and multiplying by the standard deviation or volatility of B and multiplying by the correlation between the two, and I'll just do rho of A and B. Because you'll notice I do have, of course, the standard deviation of A and B, and but I don't have the correlation. Although I could deduce it, having been given the covariance, right? I could figure out here that my correlation must be equal to 0.015, the covariance, standardized or divided by the product of 0.12 multiplied by 0.18. And I think I got about 0.70. I think that's why I changed the assumption. So I could get that last term in one of two ways actually, but I want to make sure to include it. And if you did that, pretty sure you should get here 0.022. And then just we want to remember in that calculation that we're calculating a variance such that we need if we want the standard deviation or volatility, the more intuitive measure, we need to remember to take the square root of it finally. In that case, we'll get just shy of 15% standard deviation here. Okay, so I'll eliminate all that. And here again, we can make use of a gut check. We only have two stocks. They're not exactly equally weighted, but their standard deviation of 12 or an 18. Probably the standard deviation should fall somewhere between 12 and 18. If these were equally weighted and the correlation were 1, then it would be right in the average. But the correlation, an imperfect correlation and diversification benefit is going to alter that relationship and make it more dynamic. So that's just more of a guideline that might be useful for our units. When we get 0.02 in the context of these volatilities, it's a reminder we don't quite have the standard deviation yet. So for Bayes' formula, that's actually a whole big topic that's interesting in its own right. And by the way, I have several videos in on the channel on different applications of Bayes' formula, including some more advanced applications. But here is the version that's in the syllabus, CFA syllabus. The probability of an event conditional on some information that we've received here is, you can see, is itself equal to the conditional probability, but notice it's reversed here, of information given the event divided by unconditional probability of the information itself multiplied by probability of the event. So how might we get there? Well, the way that I think about that is if we took a unconditional probability, I'm just going to abbreviate, of information and multiplied by the conditional probability of the event given the information, that is itself the joint probability of information and event. And we could solving for the conditional probability of information given the event is equal to here a joint probability of information and event divided by, see, the unconditional probability of the information. So we just expressed here a conditional probability as equal to a joint probability divided by an unconditional probability. So that's a basic, to me, probability relationship. And now we just expand on the numerator here as itself a joint probability, but we approach it in the other direction as the probability of the unconditional probability of an event multiplied by the conditional probability of information given the event, that divided by the same denominator, unconditional probability of the information. And so that here allows us to solve for this conditional probability as a function of this conditional probability, which reverses the information in the event. And you can see this here, that is this same expression here. And so an application here would be, I'll take that off, would be this sort of problem where we have a set of assumptions, and the set of assumptions are here. We have basically two sorts of variables. A company, its quarterly earnings, the earnings per share either exceeds, meets, or falls short of the consensus. And notice we might be given three probabilities here. And these are unconditional probabilities. They're not conditional on the other variable, which is the company expanding or not. The probability that the EPS exceeds consensus is 45%. And then we also have a 25% probability that the EPS meets consensus and a 30% probability that it falls short of consensus. So these are three unconditional probabilities, and they are analogous here to the event, but they are unconditional events. So that's right here. The probability event here could be any one of these three unconditional probabilities. Then we're given three conditional probabilities, and these are all the probability that the company expands conditional on different events with respect to the EPS. If the company's EPS exceeds consensus, right, so think it's doing very well financially, there's a 60% conditional probability that it expands. If the EPS only meets expectations, there is a 30% probability the company expands, and if the EPS falls short, there's only a 10% probability. So notice again, these are conditional probabilities. The probability that unlike these which are unconditional, the probability that in each case that the company expands, conditional on different EPS outcomes, such that that's all we need to be given. We could compute the unconditional probability that the company expands because we're given here these three conditional probabilities. The unconditional probability the company expands is simply a weighted average of these three events. 45% probability EPS, this right here, right? 45% probability that it exceeds consensus multiplied by the conditional 60% probability that the company expands if it does, plus 25% probability unconditional EPS meets consensus multiplied by then the conditional probability that the company expands, 0.3 plus, finally 0.3 multiplied by 0.1. That together gives us 0.3750, the unconditional probability that the company expands, and analogously, that's the probability of information here on the denominator. It's 0.375. So then we could apply Bayes to answer this question and notice how the conditionality is reversed. We've already been given the conditional probability the company expands. Under here, different outcomes with respect to EPS, which is the event. Then we might be asking, what if we just observe that the company expanded? What then would be the probability that that is our information? What then is the probability that the event happens that the company expands? In other words, what's the probability that EPS exceeds consensus conditional on the observation that the company expands? See how it switches the conditionality? And we aren't really given that right away directly. We would have to infer it here with the Bayes theorem. So what we have is the probability of EPS exceeds conditional on company expands, which is really the probability of the event conditional on our information. And you can see here, well, that equals the probability of information conditional on the event, see the reversal, which here, that is this value right here. The probability that the company expands conditional on the EPS exceeds. So that's my 0.60. And I could multiply that here by the probability of the event. And the probability of the event is the probability that EPS exceeds consensus, which is 0.45. That's a multiplier here. And divide that by the probability of the information, which is the probability that the company expands, 0.375 in the denominator. So I have here in the numerator 0.6 multiplied by 0.45 divided by, that's not very well written, sorry, 0.375. Here will get me my 72% is the conditional probability that EPS exceeds, conditional or given on the observation that the company expands. And see how by using Bayes, we're able to make that determination of a conditional probability using here this other sort of reverse conditional probability. So then finally, quickly, in terms of some topics, multiplication rule. If we assume that one task can be done in n sub 1 number of ways, and a second task, given the first, can be done in n2 number of ways, and a third task, given the first two tasks, in itself be done in n sub 3 different ways. For a k number of tasks, then the number of ways the k tasks can be done is by simply multiplying those n together. But we just want to be careful as to whether we are counting down as we assign tasks. So, for example, let's say we have 4 analysts and we want to assign them 4 different industries to cover for research. So if we go to the first analyst, we have 4 industries from which to choose. And so we give that analyst one of the 4 industries. Then when we go to the next analyst, one industry's already been assigned, so there's only 3 ways to assign, only 3 industries left. And the third analyst, there's only 2 left to industries. And by the time we get to the fourth of 4 analysts, there's only 1 industry left and therefore only one way to make that assignment. So in that situation, these n's are declining, and we have n times n minus 1 times n minus 2. So that's so common and realistic that itself is a factorial, right? N exclam is n multiplied by n minus 1 multiplied by n minus 2 and so on is n factorial. Then the multinomial formula is used for the labeling problem. And so that's when we can label each object in a group into a different category. Consider we might have n items. Each can receive one of k labels. And the number of items that receive the label 1 is n subscript 1. The number that can receive label 2 is n subscript and so on. Then the multinomial formula is used to tell us how many different number of ways are there of doing this labeling. So for example, if we have 10 mutual funds, of which 3 are labeled as high risk, 4 are labeled as medium risk, and 3 are labeled as low risk, then the total number of ways we can do that labeling, that is to say, notice we have high, medium, and low, 3 categories in which to label, and we know how many are going to be in each category. The number of ways to label is 10 mutual funds, 10 factorial in the numerator, divided by here the product of 3 factorial, 4 factorial, and 3 factorial. And so this can get rather large, in this case, 4,200 different ways to label according to that multinomial formula. Finally, combinations and permutations, very popular and common. Combinations, the number of ways of choosing R objects from a total of N objects when the order does not matter. So that's also here called a binomial coefficient. N choose R. How many different ways are there to choose R objects from a total set of N objects is given by the binomial coefficient itself. Here is N factorial divided by, here you can see the product of N minus R factorial multiplied by R factorial. So for example, an analyst wants to buy 3 stocks out of 5 stocks. So that is, choose 3 out of n equals 5. What are the total number of ways he or she can do that? That's 5. Among 5, choose 3. And you can see it's n factorial, 5 factorial divided by n minus r is 5 minus 3, or 2 factorial multiplied by 3 factorial. And the only thing I would say about that is it's just very good to be able to know you can cancel. Right, so if I have 5 factorial over 3 factorial, let me write that over here. If I have 5 factorial over 3 factorial, right, we know the 5 factorial is 5 times 4 times 3 times 2 times 1, and the 3 factorial is 3 times 2 times 1. And so these cancel. So 5 factorial divided by 3 factorial is itself 5 times 4 because the rest cancels. So 5 factorial over 3 factorial, well, what I, just for purpose of rearrangement, this here is 1 over 2 factorial multiplied by, we can see 5 times 4, or 1/2 of 20 or 10. But realistically, in some cases, the solution is quite simple, because we might end up with something like 24 factorial over 23 factorial. And I've gotten questions in my forum where people will say, my calculator doesn't handle that large of a number. I'm not sure if I got that exactly, but at some point the number 20 factorial, at some n factorial, the number is simply too large. But here, we don't need a calculator for this problem here, right? 24 factorial equals 24 times 23 factorial divided by 23 factorial, and we can just see they cancel. This must equal 24, so we want to be handy in doing that. And finally, then related to the combination is the permutation, but that's when the order does matter. So here, the permutation, the number of ways of choosing R objects from a total of N objects when the order in which R objects matter. So if we are counting order permutation, if you think about it, that number needs to be significantly higher. N permutation R is given by N factorial divided by quantity R, N minus R factorial. What was the only difference there? Well, the only difference was we don't have that R factorial in the denominator, and so that itself is going to be the ratio between the permutation and commutation. So if we come back to that previous question, an analyst wants to buy 3 stocks out of 5 and rank the stocks in order. What are the number of ways he can do that? So that question is different, right? Because in the combination question before, if the analyst goes and picks, let's see, 3 stocks, Microsoft, his 3 stocks are going to be, let's say, Microsoft, Google, and what's my other one going to be? How about Amazon? A little late for that, but I think, but those are the 3. In the combination, previous problem, it doesn't matter what order he selects them. But here, if he's going to rank them, then this here might be a ranking where implicitly Microsoft is first, Google is second, Amazon is third. That is a different event, really, than ranking Amazon first, Microsoft second, Google third. In combinations, those are the same and only count once, but in permutation we have 2 different events here, and so we count them as 2. So we have a lot more permutations, and in this case applying the formula 5 factorial divided by 2 factorial, and by the way, applying that what I just did before, if I want 5 factorial divided by 2 factorial, right, then it doesn't, well, I'm going to too much trouble here, but I can see that it's 5 times 4 times 3 times 2 factorial divided by 2 factorial, so that these cancel, and I have 5 times 4 times 3, or 60, and I get my permutation. 60 if the order does matter, and then by the way, what was that ratio? Well, remember, the only difference in the formula here was the R factorial in the numerator. What was that? What is R? R is 3. The 3 stocks, so it's 1 over R factorial is 1 over 3 factorial, which is 1/6, and in fact, if we take the 60 then, right, and multiply by 160, we get 10, and that was the number of combinations. So it's a factor here of 1/6 or 6 times as many permutations, because in permutations the order does matter. So that's really an end of discussion here. Portfolio, expected return, and variance, and also the additional topics and probability covered very quickly. But if you're studying for the CFA, I hope the video is helpful. If the video is helpful, it's a long video, and you stayed with me this long, then please do subscribe to the channel, and you'll get notified of future videos. Thank you.